So
We are already live.
okay, but the students are not there. So the challenge the student had is student attendance. Okay, so they assess they saw the course. When they click on it, it was not listed among the courses they can configure so they couldn't submit their attendance. It's not good. I think it's
Are they saying that the course is not listed?
the course was listed. But when they click on it, I'm going to do that now so that you can understand what I think it's better to tell you. So here we are. The course is listed. So that's what they have to click on to submit attendance. Click on view submit attendance. Course attendance. It's not there. So that's what, because a number of them that know me have to send to a submission.
So I can see one that we
are yeah, I told them that you'll be sorted this morning.
Did you receive the system generated code from your mail?
Today?
You received a lot of because it's every day. I'm cautious to what the system will send. I shall have for fun.
Okay.
The email there.
Oh, we went on the past university mail. Okay, I've seen one, 6:45. We sent some about an hour ago.
Okay.
And
our code demand classes.
TELEPRESENCE, course.
Thank you.
Okay.
It's really
working with you.
I said we see you, but
I see the lecture more than 11. Just perfecting everything. Truly, okay, strong. That's writing stuff.
That's what we have to do. Just to show that. Yeah. We have to come from the information. They want to connect to
This piece of mind.
you can see this before.
Oh,
You see this
space in there. We went to space in there.
this one is
So let's go to the last one.
the price.
It's not
Yeah, it is. Because
Okay, let's
instead of for example, after this.
It's too thick. I'm changing. Wow. It's okay. I mean, the most fun thing is that the follow on teaching. Later will be okay. Yeah.
It seems it's very smooth.
Yeah. It's more like kids. Oh, beautiful. So let's see.
So,
This is too.
you just go up. That's the next.
Okay, the next one. Alright.
But you are very super sensitive. If you force anything out to just the mouth here.
Because the pen is on. Because the pen is on.
So let's see now. Let's see the pen is on. The eraser. So let me just
Okay, even where we have the type something down, you can write on that same page.
you can annotate
So
that point out that this is beautiful.
we should label it. We should label it letter 1, letter 2. No constant 2. No constant 2. Letter 2.
So Mama actually and probably
With 3, yes. That's I have them with. Yes. Let's have one.
So
This is 1, that's 1, 2. With the real until now. It doesn't contact 2.
plus
3.
if you really don't
No, it's 3. That's a partial fraction. That's why I label it so that it will be easy to associate it to each other.
so when we submit or they
They
didn't
couldn't submit attendance system because they couldn't see the course.
and so
They were willing, they were desirous to go. After they came to meet me in the office, a number of them escape visa, couldn't submit.
Because the others of thousands of one daily. Thousands of other
And they just
submit.
they know just click on any course. Only company or that's it.
When we sort it based on the fee
of the course. Exactly.
Received a copy of the attendance code. As I received a copy of the attendance code.
Okay, the code. And you've written it, sir.
That's what I'm saying. I've written the damn thing for you to make it
Okay.
easy. Especially nothing it wasn't because of the lecture. This thing for Francis. No, because I was.
Any people I came along.
But you try.
Get reaching me.
Because I wanted to have it so.
Be present. Now, I want to drink. I don't look. I was almost fainting. I'm pain. The cafeteria, the time you know, Bamba, meters. That's the perspective.
You send the CD.
Me,
So you send the
because your sister, oh, I'm doing here.
Hey, but I mean, so no multitasking and doing all this together. Send the
Say that to us, nature.
Now, still like
Is it on share this one?
ó ṣe àpèjì ní èrò tí wà ní déètì ọ̀rá.
No, first send is saying it is not. No, also share it.
Just trying to
Quel est l'email adresse?
TELEPRESENCE is Gmail. Is
It's not. The address telepresence.ace.gmail.
at Gmail.
Okay, at Gmail. Send the block constant tree. Let me send the block constant free. Let me send the block lecture and it comes to partial prayer. Check to me.
They've seen that. I'm not saying that we did, but also
Okay, as a slide. Kò sí wà the challenge mo ní pẹ̀lú nǹkan tó wà lórí fún mi sí pé àwọn ẹbí ṣe àṣìbí ẹ̀.
Yeah.
Yes,
It's,
sir.
it's sentence. That refresh give you the key. It is sending. Go send it. It is sending. I'll check my sends messages. Go send it. PJ, then you name on it. I don't know. PJ, you can always see. Go send it. Ṣé èwo ló tún wọlé ń bẹ̀ báyìí? Kò sí 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 èwo tí wọlé náà. Àwọn tí mo ti ṣe ẹ̀ lè bẹ̀rẹ̀ pẹ̀lú àwọn ókèdè àná for today. Je ne sais pas du tout, mais le plus c'est pas compte. Comment c'est? Souvent. Logitronics, Logitron, Logits, Logitronics, and Logitronics. Send money. Okay, send maybe it's my phone. I don't know. Maybe you send it from your own phone to your mail. Let's see. No, okay. Yes. Share to. Okay. What's your name? What's your name? What's Sunday? What's it? What do you mean? Send the two classes for today. Gmail, two. And not tomorrow morning. This testimony is only. Yes. Share. I'm going to feel the Instagram account share. Fi projet wa sórí ibi ìkẹ́.
Yeah, see, it's something we can do. I don't know.
No, please go ahead. Go ahead.
Yes.
Because already we are live.
Yes.
Ẹ ti connect Zoom.
Just connect.
Mi ò rí.
Okay. Okay.
ti ṣe tìǹtì ó ti wo zoom báyìí.
wọ́n ti mú yẹn. Ọ̀wé hàn. What is this crashing?
Crashing.
Zoom.
Okay.
Okay. Yeah.
Good morning, students. Just hold on for a few moments. Some comments. Thank you.
Prof. With this?
Yes.
So I have to see that.
Yes. I'm going to that.
My pad thing. Okay. I can see right on this too.
But you should be able to write. See, it's not unless you type on this one.
So really, so I won't be able to write there.
Yes, you want to speak in it while you're doing
Okay, on mute.
Stop.
Huh?
Why will you stop?
Okay. So to start now.
You can start. But if you want us to, if you wait for a few minutes, we person to do it.
Time till now.
Oh, yeah. I see.
Good morning once again, everybody, and you're welcome back to class. Again, let me apologize for the slight delay. It's due to some logistic issue. All right, so yesterday we looked at the how to calculate the concentrations of species at equilibrium using the ICE table. And of course, having determined the concentrations of the species, then of course we can write the expression for the equilibrium constant and then slot in the values obtained to calculate the equilibrium constant. So today we will continue by looking at the equilibrium constant again. We are looking at the characteristics of the equilibrium constant. I think I did mention this briefly yesterday, but of course, let me uh, reiterate it again for a better understanding. Now, since the equilibrium constant is determined by uh, the products of the concentrations at the numerator and the concentrations, divided by the concentration of the denominator, you find out that if the numerator is I, then the equilibrium constant will be greater than 1. In one word, since what we have as the numerator are the products, and for equilibrium constant to be greater than 1, we implies that the equilibrium favors the production of the formation of the product. That is to say, the equilibrium is shifted to the right, that is towards the equilibrium. Now, if the equilibrium constant is less than 1, the implication of that is that the denominator is greater than the numerator. And that therefore implies that the formation of reactant is more favored than the product. So therefore, equilibrium will shift to the left, favoring the reactant. And that possibility is when equilibrium constant is equals to 1. It then implies that the concentration of the product and the reactant are the same, at this point. And that is to say the numerator is equals to the denominator. And at that point, we say the equilibrium is a static equilibrium. Static equilibrium. All right. So that's one of the properties or characteristics of the equilibrium constant in terms of the magnitude. Another thing of interest about the equilibrium constant is how do we express it as a function of the stoichiometry of the reaction. For example, look at the formation of ammonia from nitrogen and hydrogen at a particular temperature. We're told that the equilibrium constant for the reaction is 0.013. All right, for the balanced equation here. So the question is, how do we relate of we have the for the original equation N2 plus 3H2 to give 2NH3, the equilibrium constant is 0.013. Now, suppose the equation is written in these forms. Here you have half N2 plus 3 over 2 H2 to give 1 mole of NH3. A very careful look at this A and the original equation, which you have here, will show that the A in this expression was obtained when the original equation is divided by half. You know, in the original equation, you have N2 plus 3H2 to give 2NH3. So you divide through by 2, you're going to have what we have here, half N2 plus 3H2 to give us NH3. How do we compare the equilibrium constant for this new equation, this new form of expressing the reaction between nitrogen and hydrogen to give ammonia to the original balanced equation? All right, so going back again to the original balanced equation, we find out that the equilibrium constant, so if you write the expression for the equilibrium constant for the original equation, you find that the equilibrium constant is equals to the constant of NH3 raised to power 2 divided by the product of the concentration of N2 and that of H2 raised to power 3. And that is what you have in this equation. Now, that particular equation, if I decide to find the square root of it, if I find the square root of this equation, then we'll find out that the equilibrium constant for A. Okay, let's write the equilibrium constant for A. All right, the equilibrium constant for A, of course, had been written as finding the square root of the original equation, and so therefore it means therefore that the equilibrium constant for A would be the square root of the equilibrium constant for the original balanced equation. I don't know. I hope that is understandable, or should I go through it again for you to understand? I want you to please listen and listen well. Look at equation A and look at the original balanced equation. For the original balanced equation, the equilibrium constant is expressed as the first expression under solution here. And I want everyone to please put pen to paper and confirm that this is correct from the balanced equation that is displayed here. Okay, everybody please try and put pen to paper and let us see what you're going to obtain as the expression for the equilibrium constant. I'm sure you're going to get the first expression here. Okay, now let's go back to A. Let's get the equilibrium constant for A. The equilibrium constant for A will be equals to NH3 divided by N2 raised to the power of half and 3 over H2 raised to the power of 3 over 2. And that's what you have here. Now, when we compare this Ka, which I've labeled Ka, because we are looking at equation A here, if you compare that to the equilibrium constant for the balanced equation, what relationship can we see? Relationship can we see? It simply implies that if you look at the original equation here and the Ka is simply the square root of K. So the summary is that when you have the stoichiometric coefficient in a balanced equation, the corresponding equilibrium constant will be the square root of the equilibrium constant for the balanced equation. Now let's look at the next one. For B, when we compare B with the original balanced equation we have there, you will find out that we have reversed the original balanced equation because we are looking at formation of ammonia, not the dissociation of ammonia. But B here is showing us the expression for the dissociation of ammonia, which is, of course, the reverse of the formation of ammonia. Let's write the equilibrium constant for B. Everybody, please put pen to paper. Write the equilibrium constant for B, and let's see what you're going to obtain. Let's do that quickly. I'm sure we are on it. All right. It's here displayed as KB. That's what we have here as KB. I'm sure we can all see it. Now, KB is simply equals to the concentration of N2 multiplied by the cube of the concentration of H2 divided the square of the concentration of NH3. Okay? Now, when you compare that to the original equation for the formation of ammonia, you will see that the new equilibrium constant is just the inverse of the original equilibrium constant. Something is. Okay, thank you. So, so you can see here what that means is that if an equilibrium process is reversed, the corresponding equilibrium constant will be the reciprocal of the original equilibrium constant. That's the implication of that. Now I want to now see. I want to use A and B to explain how the equilibrium constant vary with the stoichiometry coefficient in the balanced equation. I want you to see what you can do with C and D on your own. I want to explain A and B. The solutions are here, but the way to learn this concept is to put pen to paper and try to see what I've been taught. Can I use it to solve problems on my own? So without looking at the solution that I've provided here for C and D, I would like you to, on your own, put pen to paper and obtain the equilibrium constant for C and D in terms of the equilibrium constant for the formation of ammonia that we started with. Like I said, the solutions are here, but I want you to give it a try on your own before looking at the solution. Okay? If you're able to do that successfully, then you're already gaining a mastery of these concepts. Okay, now let's now summarize everything. Of course, I've said that in passing, but of course, I've put it here again. So the result can be summarized as follows. The equilibrium expression for a reaction written in reverse is the reciprocal of that for the original reaction. That, of course, we have concluded on. Then, of course, when the balanced equation for a reaction is multiplied by a factor, whether it is by half or by 2 or by whatever factor, the new equilibrium constant will be the original equilibrium constant raised to the factor to which you have multiplied it with. Okay, so that's what we call how the equilibrium constant vary with concentration. All right. Now, like I told you at the commencement of this lecture, that chemistry is a quantitative course, and you are not going to have a mastery of anything that has to do with calculation without you putting pen to paper. So we are now where we're going to see how to solve problems with equilibrium. So I have this slide, which I've titled Solving Equilibrium Problems. Now we have this equation. We have hydrogen gas reacting with iodine gas to give hydrogen iodide. And we have the balanced equation already. All right, so for this reaction, the concentration at a particular temperature in a certain experiment are as given in mole per dm cube or mole per liter. So we have H2 at equilibrium. So in this case, this is a very simple question. We are given the concentration of all the species at equilibrium. So the question is to calculate the equilibrium constant for the reaction as written. So as written, the expression for the equilibrium constant will be equals to the concentration of Hi raised to the power of 2 divided by the product of the concentration of H2 and I2. And that is what you see displayed here, which I've written for you. Slotting in the values at equilibrium for all the species will give us the expression there. For hydrogen iodide is 1.02 to the power minus 2, and so that becomes 1.02 to the power minus 2 raised to the power 2. For hydrogen, that's 8.62 to the power minus 4, and for iodine is 2.63 to the power of minus 3. A careful punching of the calculator will show you that the equilibrium constant is equals to 45.9. Now, like I said, we don't have to bother your head about the unit. Yes, because equilibrium constant, the unit could vary from one form to the other. For example, in this case now, this is a unitless equilibrium constant. Why is it unitless? You have Hi raised to the power of 2. So that is mole per dm cube times mole per dm cube as the numerator. In the denominator also, you have H2 mole per dm cube and iodine mole per dm cube. So you also have mole per dm cube times mole per dm cube. So the units will cancel each other. And of course, Kc in this case will be unitless. But it's not in all cases. For example, the ammonia case, the formation of ammonia, we have a unit that is per mole square dm raised to power 6. Okay, so since equilibrium constant unit can vary, it is always advised to drop the unit. Okay, so we don't really take the unit into account when you are writing the value for equilibrium constant. I want to explain that. We are asked to calculate the value for the reverse reaction. And as explained in the previous slide, when you reverse a reaction, the corresponding equilibrium constant will be the reciprocal of the original equilibrium constant. So the value you are going to obtain here will be 1 over 45.9. 1 over 45.9. And that is the value as displayed on the screen for you. All right, so let's make progress. This is one of the simplest questions you could ever encounter. But let's look at more challenging question. In this question, next one says, suppose that for a synthesis of hydrogen fluoride from hydrogen and fluorine, 3 moles of hydrogen and 6 moles of fluorine molecule are mixed in a 3-liter flask. The equilibrium constant for the synthesis reaction at this temperature was found to be 1.15 to the power of minus 2. What are the equilibrium concentrations of each component? All right, so we are going to write the balanced equation for the reaction between hydrogen and fluorine, just as we did for hydrogen and iodine above. Hydrogen and fluorine molecule combining together will give us 2 moles of hydrogen fluoride, and that's the balanced equation, as you can see. The equilibrium expression, of course, will be equals to HF raised to power 2 divided by the product of H2 and F2 concentrations. And we are told that to be equals to 1.15 to the power of minus 2, please. It's minus 2, not 2, please. Okay. Now, the first thing, what we need to do here, let's determine the initial concentration of the reactant that were mixed together, hydrogen and fluorine. The various moles were mixed in a 3-liter flask. So the concentration of hydrogen will be equals to 3 moles divided by 3 liter, and that will be 1 mole per liter, or 1 mole per dm cube. For fluorine molecule, that will be 6 moles divided by 3, and that will be 2 moles per liter. So we know the initial concentration of each of them. Now let's set up our, and of course, initially there won't be any HF. So the initial concentration of HF is 0. Now let's set up our ICE table, ICE table. I call it ICE table. All right. So this is our ICE table, ICE. I standing for initial, C standing for change, and of course E standing for equilibrium concentration. Okay, so you can see there that are tabulated. We have H2 plus F2 to give 2HF. The initial concentration of the reactant, 1 mole per dm cube for H2, 2 moles per dm cube for F2. Now, before we can understand the change that occur, we need to understand the stoichiometry relationship between the reactant and the product. From the balanced equation, we can see 1 mole of H2 is reacting with 1 mole of F2 to give 2 moles of HF. It implies, therefore, that when X moles of H2 is consumed because it's a reactant, then X moles of F2 also will have been consumed because the mole ratio is 1 to 1. So it's going to be X to X. Now, then, since the mole ratio, the mole of HF is 2, it then implies that by the time X moles of H2 is consumed, X moles of F2 is consumed, 2X moles of HF will have been formed. And of course, the concentration at equilibrium will be equals to, for H2, 1 minus X, for F2, 2 minus X, and for HF, 2X. All right, if you substitute these equilibrium concentrations into the equilibrium expression that we wrote on the last slide, we find out that the equilibrium constant will be 1.15 to the power of 2, okay? It's power of 2, not minus 2. All right, please help me change that in your notes, please. Let's go back there. It's actually 1.15 to the power of 2. Please take note of that. Please let me change this in your notes to the power of 2. Okay, so if you have done that, if you have done that, shall we then continue? All right, so putting the yeah. All right, let's pause a bit now. Let's please take the attendance for today's lecture. So please go to attendance, whatever device you are using, whether it's a phone or a laptop. You have already entered to the platform, and on the platform you select the course, Chemistry 101, and if you select that, you then see where you can select the course that you are attending now. Okay, let me wait for all of us to take time to do that. I want to believe we are all there. Okay, if we are all there, the codes are the code is now everything in caps, in capital letter. N to W R P. I'll repeat it again. N as in Nigeria, capital N. 2, figure 2. W as in West Africa, West as in West. R as in righteousness, R. P as in palm wine or palm, whatever. All right, so everything in capital. So I want to believe we already are logging our attendance. All right, so I'll continue with my class. All right, so if we substitute the values as obtained from the ICE table, for HF is 2x, and so since is hf squared, so it will be 2x raised to the power of 2. Then, of course, we have 1 minus x for hydrogen and 2 minus x for fluorine. To solve for x, of course, we perform the calculation here. Now, this will give us a quadratic expression. This will give us a quadratic expression. And of course, remember your formula for quadratic equation. The quadratic formula, that's what we call the almighty formula. X is equals to minus b plus or minus square root of b squared minus 4ac all over 2a. All right. Let's see what is a. Let's go back to the equation. A here is the coefficient of a squared, and that's 1.11 to the power of 2. B is the coefficient of x, and that is minus 3.45 to the power of 2. And of course, C is the constant, which is 2.30 to the power of 2. All right, let's put that back into the quadratic expression. If you do that carefully, we are going to obtain two values since it's a quadratic expression. Okay, so we have a value 2.14 and 0.968. Now, how reasonable are these values? Now let's go back. Which of these value is the reasonable value? Now let's go back to the highest table, or let's go back to the information we're given. Let's go back to the highest table. So we have x is 2.14. We have x is equal to 0.968. If we go back to the highest table, we can see the first one, 2.14, is greater than the initial concentration of either hydrogen or fluorine. And that cannot be possible. There is no way the value we obtain will be greater than the initial concentration of the reactant that are being used up to form certain products. Okay, our expectation will be, since the reactant are being used up, there is no way the value of X can be greater than the smaller of the two, which is the concentration of hydrogen, which is 1.00 molar. So therefore, the value 2.14 will be grotesque, will be an unreasonable value. So we discard that. Now let's look at the other one. X is 0.968. Yes. Now that's less than 1. Okay, so that's a reasonable value. So our value in this case would be equals to 0.968. 0.968. So I want to find out the value of X. The question asks us to determine the equilibrium concentrations of each of the species, the reactant and product. Since we know hydrogen is 1 molar, and initially, and of course, X, what is left of it, what have been consumed of it rather, is 0.968. It then implies that at equilibrium, the concentration of hydrogen will be 1 minus 0.968, which will be equals to 0.032 molar. Similarly, for fluorine molecule, the initial concentration is 2.0 molar, and 0.968 of it are being consumed. So therefore, is left at equilibrium will be equals to 1.032. Now for hydrogen fluoride, 2x of it is at equilibrium. So that will be 2 times 0.968, and that will be 1.936 molar. Now, having obtained the equilibrium concentrations of each of the species, you want to be sure that your answer is correct. Slot in this value, the equilibrium concentration we've obtained now, slot it back again to the expression for equilibrium constant. Then you get a value of 1.13 to the power of 2. Of course, the value we're given is 1.15 to the power of 2. We're getting a value of 1.13 to to the power of 2. Of course, the little difference in the value will be as a result of the approximations made here and there. Okay, and so this is very close to the answer, and that means that this is the correct value. I mean that means that your calculation is correct. All right. Okay. Uh, so we almost to the end of the lecture, but let me quickly do a recap of what we have done today. A quick recap. Let's go straight. All right. So the first thing we looked at is the characteristic of the equilibrium constant, the magnitude of the equilibrium constant. The first thing we looked at, when the equilibrium constant is greater than 1, it means that you have more products than you have reactant. In one word, the equilibrium position shifts to the right. When the equilibrium constant is less than 1, it means that the concentration of the reactant is more than that of, and so equilibrium shift to favor that means that the equilibrium favor the reactant. Okay, so it shifts to the left. But of course, when equilibrium constant is 1, it means that we have equal concentrations of the products and the reactant. And I said that is a state of static equilibrium when K is equal to 1. Please take note of this. Take note of this important information so that you can distinguish between dynamic equilibrium and static equilibrium. All right. Then how does equilibrium constant vary with the stoichiometry of the reaction? The summary of that is when the equilibrium process is reversed. When you reverse the equilibrium reaction, then of course the corresponding equilibrium constant will be the reciprocal of the original. When you multiply the balanced equation by any factor, then the new equilibrium constant will be the original equilibrium constant raised to the power of the factor to which you multiply the original equation. Okay, that is summary of that. Then, of course, we've looked at some simple equilibrium problems. This one is very simple. Now, the one that will be a bit challenging is this, where you will need to solve a quadratic expression. And in solving a quadratic expression, you're going to get 2 answers. Since you're going to get 2 answers, you want to ask yourself which of these is more reasonable. Which of this is the reasonable answer? To be able to know which one is reasonable, you compare the value you obtain to the initial concentrations of the species given. You compare it. And if you compare it, you find out that if the value obtained as X is greater than any of them, then of course that will be an unreasonable solution. Is the one that has the value that is less than the least or the lesser of the concentration of the 2 reactants will be the reasonable answer. So that's all we have done today, and I hope that should be understandable. And before we go, let us enter. Let us fill the attendance again, please. So please go to the attendance. Okay, I hope we are all there. Please quickly, let's all go to the attendance. I know some of you are writing what is being displayed, so you could you're taking your time, but please let's hurry up and write. Don't let us write at the speed of snail. Huh? Okay. All right. So are we all there? Okay. So the second attendance, the code for that is N figure 9. Y as in yes. Okay. Y C as in congratulations, all in capital. And J, joy. Joy. Okay. Nigeria, 9. Yes. Congratulations, joy. N, 9. Y, C, J. Well, thank you. I'll see you again tomorrow. Please, if you are in group A, there's no group A or group B as far as this course is concerned. All right, please. Henceforth, at least for this period that we're doing online teaching, both A and B are meant to be together. So we'll continue tomorrow by the grace of God. Actually, I will time to land meeting. I don't know it offhand, but I'll check it. Just hold on. Let me. I know you'll probably be in a hurry to go for another lecture, but while you are doing that, on the way, I know you are probably on your way to for Phys 101 or 105, as the case may be. All right, let me quickly check the time for tomorrow. Just hold on a bit. The next 1 minute or so. Open. Yeah. Nothing be more frustrating than you open something and it's not open. So as you're walking to the lecture or just let me just check. I don't know why this thing is not. Come on, show you. All right, so tomorrow is 9 a.m., please. 9 a.m. So we'll see you tomorrow by 9. Thank you, and have a great day. The computer just sent the time to me.